The Hoover Dam, America's largest hydraulic engineering project, required the flooding of surrounding towns to ensure its construction success. Why was it so crucial to build such a monumental structure? And how was the Hoover Dam successfully constructed in an era with less advanced technology? Subscribe to our channel and don't miss out on the upcoming exciting content. Imagine a dusty construction site, where a fleet of heavy excavators roars to life, each with a massive bucket holding over 30 cubic meters. These powerful machines effortlessly tear through hard rock and soil, not only digging deep into the foundation of the Hoover Dam, but also acting like sweepers, clearing away debris and rubble. Following this, loaders, with their efficient loading capacity and flexible maneuverability, quickly transfer these materials to transport vehicles, which carry them to designated locations. This groundwork laid a solid foundation for the stability of the dam, ensuring the construction proceeded efficiently. On the Hoover Dam construction site, nothing was more eye-catching than the rumbling Caterpillar track-type tractors. These steel behemoths, hailing from Illinois with over 500 horsepower and exceptional durability, became the main force in building the dam. The Caterpillar 60 track-type tractors were not only the pinnacle of technology at the time, but also the backbone of the dam's construction. Their immense power allowed them to easily drag heavy loads, navigate complex terrains, and meet various operational needs. They played a crucial role in digging diversion tunnels and ensuring the Colorado River flowed smoothly around the construction site during the building process. These tractors also transported massive pipes and heavy construction materials, providing solid logistical support for the dam's construction. Additionally, they were involved in stripping and leveling the topsoil at the construction site, laying a firm foundation for the subsequent concrete pouring. The Hoover Dam's concrete pouring volume was astounding, totaling 3.36 million cubic meters. To manage such a massive project, designers creatively adopted the column pouring method, dividing the dam into 230 vertical column blocks for pouring. Each upstream block measured 5 mm by 18 mm, while the downstream blocks measured 7 mm by 9 mm, with each pouring layer being 1.5 mm thick. The mixing stations at the time employed advanced automated control systems, which automatically completed the mixing process according to preset ratios. These mixing stations could produce hundreds of cubic meters of concrete per hour, meeting the enormous demands of the dam's construction. Engineers designed an efficient delivery system to transport the mixed concrete to the pouring site in a timely manner. This system included concrete pump trucks, conveyor belts, and pipes, all working together to ensure continuous and stable concrete delivery to the designated locations. Particularly noteworthy were the concrete pump trucks, with their long arms and precise spraying capabilities, which allowed them to operate smoothly, even in challenging terrains and high-altitude conditions. These pieces of equipment worked in harmony, like flowing green veins, continuously delivering the lifeblood, concrete, to every corner of the dam. The heat dissipation during the concrete pouring process was a significant challenge for engineers. Due to the dam's large volume and the massive amount of concrete poured, the concrete generated a lot of heat as it solidified. If not handled properly, this could lead to cracking or even structural damage. To address this, engineers designed a sophisticated cooling system. Cooling pipes, slender steel tubes, were embedded within the concrete to form a dense cooling network. After the concrete was poured, cold water was injected into the cooling pipes, quickly lowering the internal temperature of the concrete and preventing it from cracking due to overheating. To ensure a continuous and stable supply of cold water in the cooling pipes, engineers also designed a cold water circulation system. This system used pumps to deliver cold water to the cooling pipes, then returned the heated water to cooling towers for temperature reduction. This cycle repeated, ensuring effective cooling while conserving water resources. The Hoover Dam's success lies not only in its massive scale and advanced technology, but also in its harmonious integration with the surrounding environment. To enhance the dam's stability, the designers needed to figure out how to seamlessly embed the dam's walls into the mountains on both sides. First, they blasted away the weathered and weakened rocks on either side of the dam. In areas where hard rock layers existed, Blasting equipment was used to break and loosen the rocks. In extreme cases, if unexpected rockfalls or landslides occurred during construction, blasting equipment could be employed as an emergency tool to clear obstacles or create escape routes. Then, 2 grooves were carved into the mountainsides into which the dam was embedded. The dam's base was also embedded deep into the riverbed and tightly bonded with the underlying strata. This complex operation not only tested the skill level of the construction teams, but also demonstrated the balance and exploration of harmony between humans and nature. Afterward, in the grooves and at the base of the dam, workers used drilling machines to drill into the hard rock, installing rock anchors and injecting high-pressure cement grout through a grouting system to ensure a tight bond between the dam and the mountains, thereby enhancing the overall structural stability. These anchors, like countless invisible ties, firmly connected the dam to the surrounding mountains, collectively bearing the natural forces' challenges. The entire process of building the dam was under precise control and continuous monitoring by engineers. To ensure the project's quality and timely completion, the most advanced surveying equipment of the time was utilized, including high-precision total stations, levels, and distance meters, to measure and position every aspect of the dam's construction. These devices acted like eyes, spread throughout the site, continuously transmitting the dam's health status, providing valuable data to the engineers. For example, the total station's comprehensive positioning, which accurately measured the dam's 3-dimensional coordinates and calculated construction precision, using levels to control the dam's elevation and horizontal stability, and adding distance meters for quick distance measurement to assist workers in positioning during construction, together with the strain gauges installed within the dam, which monitored the concrete strain and assessed the dam's structural safety. The piezometers, which monitored the dam's and bedrock's seepage pressure, preventing seepage issues, and inclinometers used for monitoring the dam's tilt. These devices formed the dam's nervous system network. This ensured that the dam's verticality, horizontality, and other indicators met the required standards, allowing for a timely response to stress changes and safety conditions during construction and operation, thereby reducing risks, ensuring safe construction, and saving labor costs. The completion of the Hoover Dam not only significantly improved flood control, power generation, irrigation, and water supply conditions in the western United States, but also left behind a valuable legacy. The Hoover Dam's primary mission was flood control, and it has successfully protected millions of downstream residents and thousands of square kilometers of farmland from floods since its completion. In addition to its flood control function, the Hoover Dam is also a giant hydroelectric power plant. Its U-shaped power facility houses 17 turbine generators with an installed capacity of 2.08 million kilowatts. During the installation process, engineers overcame numerous challenges using special lifting equipment and techniques to successfully position the massive turbine generators. The dam then harnessed the Colorado River's flow, creating a large reservoir, Lake Mead, to supply water to the generators. The water flows through intake pipes into the power plant, driving the turbine generators. Inside the turbines, rotors and stators work together, converting the mechanical energy into electrical energy as the rotor's rotation cuts through the magnetic field of the stator. The generated electricity is then transmitted through power lines to various consumption areas, providing a continuous supply of clean energy to the western United States. The dam's power output meets the electricity needs of millions of households, saving billions of dollars in energy costs each year. Additionally, its irrigation system covers thousands of square kilometers of land, turning the region into one of America's major agricultural production areas. The bountiful harvests not only enrich people's tables, but also provide a stable and reliable water supply to surrounding cities. Regarding navigation, the dam's water storage function has raised the water level in downstream sections of the river, reducing water flow speed and making previously turbulent and dangerous sections safe for navigation. By regulating water levels and flow speeds, it has transformed the river into a viable waterway. Furthermore, the dam is equipped with a lock system that allows vessels to pass through smoothly, without the need for detours or complicated navigation operations. Today, the Colorado River has become an essential waterway in the western United States, providing vital support for the region's economic development. Through our presentation today, you can vividly imagine the challenges faced by the workers who built the Hoover Dam in that desolate and demanding canyon. They contended not only with cold steel and hard rock, but also with the harsh trials of nature. Under the scorching sun and amid alternating sandstorms, engineers and workers operated various types of machinery, from excavation and transportation to pouring and installation. Every step was infused with their sweat and ingenuity, leading to the Hoover Dam's outstanding functions today: flood control, power generation, irrigation, navigation, and water supply. These achievements have greatly improved the natural environment and socio-economic conditions of the western United States. The Hoover Dam stands not only as a testament to human ingenuity and a marvel in the history of engineering, but also as a model of harmonious coexistence between humans and nature. For those who are passionate about architectural technology and mechanical stories, be sure to follow our channel. For more exciting content, hit that subscribe button, and we'll see you next time.